Welcome to the chemistry module discussion. In the introductory tasks, you were asked of the basics of mole concept. You were also asked how you're going to count the grains of rice in a jar. The answer to that one is to get the mass of all the grains, then get the mass of one grain. Divide the total mass of all grains by the mass of one grain. This is basically similar to the mole concept. For this session, we are going to define mole and use molar mass and Avogadro's number as conversions between molecular and laboratory scales of matter. Atoms are very small in size and mass. There is a need for a suitable unit in the laboratory scale. This is analogous to buying rice in a supermarket. We count the rice by weighing the rice. If we know the average mass of one grain, then we can determine the number of grains of rice. We do not count it one by one, just like the atoms. Another example is when we know the mass of one mango and we know the total mass of many mangoes. Then from these masses we can determine how many mangoes there are. Example, if one mango has a mass of 172 grams, then how many mangoes are there if the total mass is 12.9 kilograms? What we can do is to divide the masses to get the answer, which is 75 pieces. Just like the atoms, we should be able to weigh it in the laboratory scale, so we could be able to count these atoms. To relate what we weigh to the number of atoms, we use the mole, which is the standard unit of the amount of matter. 1 mole is actually equal to 6.022 times 10 to the positive 23 of objects. That large value is termed the Avogadro's number, denoted by N sub A. 1 mole is an Avogadro's number of objects. This is a suitable unit because its large value is useful since even the smallest amount of matter contains large numbers of atoms. The usage of mole being equivalent to the Avogadro's number of objects is analogous to 1 dozen, which is equivalent to 12 objects, 1 pair, which is 2 objects, and 1 gross, which is 144 objects. In chemistry, we use this relationship of mole and Avogadro's number to relate the molecular scale and laboratory scale. Molecular scale pertains to the molecules, atoms, ions, and formula units, while the laboratory scale pertains to mole. 1 mole is equal to 6.022 times 10 to the positive 23 objects, and these objects are the atoms for the elements, molecules for the molecular compound, ions for ions, and formula units for ionic compounds. From this definition of moles, we can actually establish mole conversion factors for elements, covalent molecular compounds, and ionic compounds. For example, if we have the element xenon, we have 1 mole of xenon is equal to 6.022 times 10 to the positive 23 xenon atoms. For covalent molecular compounds like carbon dioxide, 1 mole of carbon dioxide is equal to 6.022 times 10 to the positive 23 molecules of carbon dioxide. For sodium chloride, which is an ionic compound, we have 1 mole of sodium chloride is equal to 6.022 times 10 to the positive 23 formula units of sodium chloride. Let us try to use these conversion factors in some examples. In this problem, we need to calculate the number of formula units of KCl given the moles of KCl. We just need to use a conversion factor to cancel out the unit of mole KCl and come up with the unit formula units of KCl. Thus, we have 1.70 times 10 to the positive 24 KCl formula units. In this next problem, we need to calculate the moles of cobalt given the number of cobalt atoms. Again, we just need to utilize the conversion factor to cancel out the unit cobalt atoms and get moles of cobalt. Solving the problem, we have 57.5 moles cobalt. We already know how to convert the molecules, atoms, formula units to moles. But we don't weigh moles. What we need to relate is moles to mass. So if we're going to talk about elements, we need to use atomic mass of 1 mole of any element. which is defined as the amount of the element that contains the same number of particles as exactly 12 grams of carbon-12 isotope. And that number is the Avogadro's number, that is 6.022 times 10 to the positive 23 carbon atoms would weigh 12 grams. So we need to know the mass of 6.022 times 10 to the 23 atoms of any element, and that would be the atomic mass of 1 mole of that particular element. Thus, the unit is grams per mole. That is pertaining to the mass, which is the grams, and 1 mole is a 6.022 times 10 to the positive 23 atoms. And this is actually summarized in the periodic table of elements. The periodic table of elements would give us the atomic mass of the elements in the unit of grams per mole. If we have a covalent molecular compound, we can get molecular mass of 1 mole of this compound by getting the sum of the atomic masses comprising the compound. For example, for carbon tetrachloride, the molecular mass is equal to the atomic mass of carbon plus 4 times the atomic mass of chlorine. We multiply the atomic mass of chlorine by 4 since there are 4 chlorine atoms in a molecule of carbon tetrachloride. Doing the calculation, we get 153.81 grams. Take note that 12.01 and 35.45 comes from the periodic table of elements. Thus, the molecular mass for this particular compound, which is carbon tetrachloride, is 153.81 grams per mole. We apply the same principle for getting the formula mass of 1 mole of an ionic compound. In general, we term these masses for 1 mole of a substance, whether elements, covalent compounds, or ionic compounds, as molar mass, and is actually expressed in terms of grams per mole. Let us use these molar masses in converting moles to mass and vice versa. In this problem, we need to convert the mass of lead to moles of lead. Thus, we need to use the molar mass of lead, which is 207.2 grams per mole. Doing that, we're going to calculate the conversion of 32.4 grams of lead to moles, and that would be equivalent to 0.156 moles of lead. In this next example, we will convert moles of calcium phosphate to grams of calcium phosphate. So this is a mole to mass conversion. So what we need is a molar mass of calcium phosphate. Doing the calculation, we're going to utilize the molar mass of calcium phosphate, which is 310.18 grams per mole, to convert the moles of calcium phosphate to grams. And that would lead us to the answer, which is 77.5 grams calcium phosphate. We can also convert mass to number of particles, that is, from macroscopic to microscopic, or the other way around, from number of particles to mass. If we want to do macroscopic to microscopic, we start with grams, convert it to moles using molar mass, and then convert moles to number of particles using Avogadro's number. Or, if we want to do microscopic to macroscopic, we start with the elementary units, convert it to moles using Avogadro's number, and then convert moles to mass using molar mass. In this example, we need to convert grams of silver to silver atoms. Thus, this is macroscopic to microscopic. We convert first grams to moles and then moles to number of silver atoms. So in that case, we need to utilize the molar mass and the Avogadro's number. Doing that, we're going to calculate 3.57 times 10 to the positive 23 silver atoms. This next example asks us to convert magnesium atoms to grams magnesium. Thus, this is microscopic to macroscopic. We need to convert magnesium atoms to moles using Avogadro's number and then convert moles to mass using the molar mass. Doing that, we should be able to calculate the answer, which is 176 grams magnesium. In this lesson, we defined mole, and we were able to use molar mass and Avogadro's number as conversions between the molecular and laboratory scales of matter.